So without any further ado, Dr. Rickles, if you'd like to introduce our presenter for today.
Yes, depending where you are in the world, it's actually the afternoon here. I wanted to welcome everyone to the NHERI Lehigh seminar series. This is a continuing event in which we have about 6 of these per year. As Tommy mentioned, my name's Jim Rickles. I'm the PI and director of the Lehigh NHERI facility. And what I'd like to do is to first introduce the speaker and then say something a little bit about the presentation. So Dr. Osman Ozbulut, I've known him for a number of years. He's a professor in the Department of Civil Engineering at the University of Virginia, currently on sabbatical in the UK. Now he has many research interests, but one of them focuses on advancing a new generation of resilient and sustainable civil infrastructure, and primarily through innovations in new types of systems, materials, and use of sensing technologies. One of these topics is related to SMA, shape memory alloys, in which they're self-centering passive energy dissipation devices that he's been looking to use both as in braces as well as for seismic isolation. Now, he serves at many, he's very active in the community in terms of his service, and he's a member of several ASC committees, including Infrastructure Resilient Division for Emerging Technologies. He's also on the Structural Engineering Institute Seismic Effects Committee, as well as the Structural Control and Sensing Committee. Also, he's an associate editor for the Journal of Intelligent Materials, Systems, and Structures. So he's a very active individual. Now, the talk today is entitled, and you can see this on the screen, Investigating Ground Motion Records from the 2023, I'm just going to say the Turkish earthquake sequence and structural context there. So it's a little bit hard for me to pronounce exact earthquake name. So without further ado, I'd like to welcome Osman and let you go ahead and proceed. Thank you.
Thank you, Jim. Thanks a lot for the kind introduction, and thanks a lot also for the invitation to the Lehigh team, putting together this webinar today. So today I will talk about the ground motion records, the recorded during this Kahramanmaras earthquake sequences, and I will look at them more through the structural context. So there have been various wonderful webinars about the effects of the Turkey earthquakes on the structures, and some of the causes for the damage on the structures, the buildings, different infrastructures, lifelines has been discussed earlier. But in webinars also there are a couple of the papers that are coming up in the literature discussing on that. Today I will do a little bit like a different thing. So we will not necessarily look at all these different factors that contribute to this really extensive damage during these earthquakes observed in Turkey, but we will look at more at regional scale and understand how those earthquakes affected certain provinces in Turkey. So without further ado, I want to start with giving a really very quick the information about the recent events in February in Turkey. So as you know, the Turkey is really very lies at a very seismically active region. And on February 6, 2023, there was an earthquake at a magnitude of 7.7 early in the morning in the southeastern part of the Turkey, followed by many aftershocks, including one with a magnitude of 6.6. But later, about like 53 miles away from this first earthquake, the 7.7 earthquake, there was another earthquake. Either you call it aftershock or a second, the main shock, but that was on a different fault, Surgui Çardak fault. The first earthquake was on the East Anatolian fault. And and that earthquake happened maybe just 9 hours apart from or away from the first earthquake. About 2 weeks later, there was another aftershock in the region. That earthquake had a magnitude of 6.4 and affected mostly the south part, the province in the south part of the Turkey. That also had really, reached a significant intensity. So that's also an important event to consider. So overall, after those events, this 11 provinces in the southeastern part of the Turkey were affected. So when we look at this region, it's about 320 mile wide, and about 250 the mile on the north-south direction, and if we want to get better understanding, a sense of this, the region, when we compare this distance from Charlottesville, Virginia, where the University of Virginia is located, it goes up to the New York City, and currently I am at University of Leeds for my sabbatical, as Professor Rickles mentioned, and when we compare this region, this 320 miles on the map, is almost entire, the United Kingdom. So the damage, or the affected region, was basically, geographically really wide, and then the damage on the buildings were also really extensive. So maybe over 230,000 buildings collapse or tag as needs to be demolished immediately or heavily damaged. So this over 230 the buildings corresponds to about 520 units or the apartments, and if you just multiply this by 4, assuming that there are 4 people living each of these units, apartments, that makes or maybe over 2 million the affected people, directly from the collapse or heavily damaged buildings. So the casualties, of course, were really high after these earthquakes, and it really caused significant, the social and economic consequences to the region. When we look at the distribution of these buildings to different provinces in the region, in this chart you see that the 3 cities, the Kahramanmaras, Malatya, and Hatay, included most of the damage or the heavily damaged buildings, collapsed buildings. The focus of my presentation will be actually 2 of these cities, Kahramanmaras and Malatya. So when we look at the earthquake, again, there was this main shock and followed by many aftershocks, but those, the main shock and aftershocks affected each of these provinces in the region differently. So to better understand that, let's look at one of these provinces, Hatay, in the south of the part of the Turkey, which is the most heavily hit city in the region. The ground motion records were really high. The intensity of the shaking was very high in this part of the country, and when we look at how this region was affected from these 4 earthquakes, the first earthquake, and then this 6.6 aftershock, and then the second earthquake occurred 9 hours later, 7.6 earthquake, and finally this 6.4 aftershock occur about 2 weeks later. You see that this for this particular site, for this the south part of the city, this first earthquake and this last aftershock was the most damaging earthquakes. But when we look at another city, Malatya, maybe the a little bit south part of the region, north part of the region, we see that this first earthquake, the 7.7 earthquake, the PJs were about 0.1 G, and then the second main earthquake, the 7.6 earthquake, was the main the earthquake in the region. So for this city, for this region, this first earthquake and this the second earthquake, where the magnitude reached to 7.6, were the main contributors to the damage in the region. So my point here is that each of these provinces affected from those earthquake sequences differently, considering this wide geographic area that is expected, but we need to consider that fact while we are also evaluating the structural damage in the region. So in this presentation, my goal is to provide you a better understanding on the seismic demands at regional scale. Again, I will be able to go over two particular provinces, Kahramanmaras and Malatya, in this presentation, and then I will try to explore the factors contribute to the extent of the damage observed in these two cities, considering the measured seismic demands. So first of all, the ground motion records that I use in this presentation were downloaded at Design Safe data center. So those ground motions were processed based on the peer protocol and provided to the larger community for the use. And there were a few for Kahramanmaras. There were a few stations where I downloaded the ground motion record, acceleration record from Turkish earthquake data center system. So those ground motions were not included in this Design Safe database. But they were in the city center for the Kahramanmaras, so I included them in the analysis. So for all of those ground motion records, I used this process corrected acceleration record and calculated the sum of the intensity measures listed here to analyze the effect of, or analyze the characteristics of these ground motion records. So those parameters includes, the sum of the times three, the parameters such as the peak ground acceleration, peak ground velocity, spectrum parameters, and as well as other intensity measures that consider the duration, frequency content of the ground motion record. So the first, we will look at the characteristics of those ground motion records in Kahramanmaras. And Kahramanmaras is a city where actually included epicenter of two of the main earthquakes, this magnitude 7.7 and 7.6 earthquakes. In the rest of my presentation, I will call the 7.7 earthquake as the first earthquake and this 7.6 earthquake as the second earthquake. So you may call those the main shock, aftershock, or we may get confused with the other the main shocks that were intensive in the region. But to avoid those confusion, I will just use this convention. The first earthquake, I am referring this 7.7, the initial earthquake, and the second earthquake, I am referring this earthquakes with a magnitude of 7.6 occurred 9 hours later. So the first, I want to show you some photos from the city center of the Kahramanmaras. Here is the Kahramanmaras city center. There was a close nearby station that we will talk later more. But I will just show some of the pictures from these different cities within the central area of the Kahramanmaras. So these pictures were taken, the original ones taken in 2022, just to promote the city, introduce the city for touristic purposes maybe. But after the earthquake, the same photographers went and took additional photos and compared the before and after the earthquake, the region. So when we look at this first location here, we see that this reinforced concrete buildings, maybe around the 10 to 12 story height, they all collapsed after the earthquake. Here is another, the street here. Along the street, the buildings here after the earthquake, they most of them, the demolished in both sides. In this side, maybe a few of them, managed to survive. And if you look at this location here, again at the city center, this building after the earthquake, the collapse, and when we look at several of these buildings here, they were also turned into the rubble after the earthquake. And similarly, another nearby location here in the city center. When we look at here, this concrete buildings, they all collapsed here. Several of these concrete buildings in this region also collapsed after the earthquake. So as you can see, the damage and the collapses has been really heavy at the city center of the Kahramanmaras. So now let's try to get an understanding. What was the seismic demands at this, the city, Kahramanmaras. So the one really good thing was that the Turkish National Strong Motion network was very dense in the region, and we have the many different stations. Both only this Kahramanmaras city, we have 22 stations, but within this wider region, there were a lot of the seismic stations, a wide network that helped to for all of us to better understand the impact of those ground motion records. So of course, here in this slide you see all the stations that were available, but not all of them recorded the ground motion records in two events. So here are like the stations that are more marked, the gray. There are no measurements, so not necessarily the same. We have recording from the same station from two earthquakes. But overall, we still have a good number of recording at the city of the Marash during both ground motion events. So when we first look at the city center, again, the buildings that I showed you were located in the city center. So if we focus on the city center and look at the ground motion records recorded during two events, if we zoom in, we see that during the first event we have 7 stations where we have data. In the second event, we only have the data from 4 stations. Here, I marked these 3 stations differently. This for the 6, 19, 18, and 21. Those 3 stations, data for these 3 stations come from the Turkish earthquake data center, while for the other earthquakes, the data comes from the design safe. They also obtain the data from the Turkish earthquake data center and processed by themselves. When we look at the soil site class of those stations where we have measurement in the city center, we will see that those stations in the northern part of the city, they have mostly the kind of a dense, stiff soil, where in the south part, this 2 station has softer soil conditions. And now when we look at the PGA, so we will go over and look at different ground motion measures for the city center. And here, first, the PGAs, the recorded PGAs for this station for the 625 and for the 624 were either about or above the design level PGA report for the region in the Turkish building code. So that is for the first earthquake. For the second earthquake, the PGAs were significantly lower for the city center. Again, these two stations had sulfur soil conditions compared to the other ones, but also these two stations are closer to the epicenter of this first event compared to the stations that were further north of the city. So of course, those stations record the ground motions in three orthogonal directions, two horizontal, one vertical direction. And the buildings may be subjected to this ground motions, any of the directions. So here I also consider the directionality and computed the ground motion records and their considering the different orientations. And I will be reporting some of those the RAD-D 100 values or RAD-D 50 values, which corresponds to the either 100th percentile or the 15th percentile of the response quantity compared for the as recorded horizontal components. So if you look at those, the PGAs, considering the directionality, we see that for some of those stations, we have slightly higher PGA levels for the RAD-D 100 measurements. If we continue and look at the peak ground velocities for those city center, the stations from the city center, we see that again these two stations really reported quite high peak ground velocities. And overall, again, the second event, the peak ground velocities were lower compared to the first, but they were at around the design level PGV specified in the Turkish building code. And when we look at this high PGV values for some of those stations, this 4624 and 4625, these two stations had the highest PGVs, those stations were again closer to the ruptured fold, and you see here a pulse-like, the record for the record measure from 4625. So that was the main reason for this higher PGVs observed for those stations, which were closer to the fold and like a recorded pulse-like motions. So when we look at the RES intensity of the recorded ground motions, again, these two stations that were located on the south part of the city center has really significant RES intensities. This 4620 and 21, these two stations here, they also have the higher RES intensities compared to the other stations observed here. And for the second event, the RES intensities were considerably lower compared to the first event. All of those stations, the significant durations of the recorded motions were between 40 to 50 seconds for both events. And when we look at the predominant period of the recorded motions, for the first event, we see, the more stations with periods below 1.5 seconds, predominant period with 1.5 seconds, while for the second event, we have those, the stations reported higher the predominant periods, especially over 1.5 seconds for most of the records. And now when we look at the spectral accelerations, that is, again, we are at the city center. We look at this, I will show you the spectral accelerations for each of these, different stations. So here you see these three stations, east-west and north-south component. And then here are these two stations for the 620 and 21. Here you see the spectral accelerations, and this design spectrum is for the city center again, for a soil site class of C, stiff soil or dense soil, and here you see the spectral acceleration for the 624 and 25, these two stations up there, and this time you see higher spectral accelerations, and for some of the periods we have even spectral accelerations higher than the design spectrum, and in that case this design spectra is actually that should be a kind of a soft soil condition. And when we look at the vertical spectrum for all those ground motion records at the city center, for higher periods, we see that this vertical ground motions had the higher spectral accelerations compared to the design spectra. And for the second event, the spectral accelerations were considerably lower. And here I marked this region 0.5 to 1.5 because most of the buildings in the city center are from 6-story, maybe up to 12-story, the buildings. But we see that at higher periods, this second event also had, for some of the station, had some, the high values. High spectral acceleration values, and here you see for the second event the vertical spectral accelerations for the city center, and when we look at the spectral velocities from all those stations in the city center, we see that the spectral accelerations were really high for these two stations, for the 624 and 25, and relatively significant for the other ones as well. And during the second event, compared to the first event, we see lower spectral velocities, but still at higher periods, we have for some of those stations, we have some high spectral velocities. And when we look at the directionality effect, so you see here the spectral acceleration for one of the station, and I show you the geometric mean east-west, north-south, and this rod D0 or the minimum one, and the rod D100, and the mean value of the spectra. So for different periods, the ground motion was polarized for certain directions. But to better assess the magnitude of this polarization, here I calculated the amplification factor using the ratio, which is the ratio of the spectral acceleration for the rod D100 to the rod D50, and that ratio was can be shown to be below 1.41, and for this case, the average values for the period range from 0.5 to 1.5, the change from, let's say, 20 to 30% for different stations. So if we kind of summarize the intensity of the shaking within the city center for the Marash during this first earthquake was at design level on average, although we observe quite high PGV values for some of the stations, especially the ones located on softer soil conditions and in the southern part of the city. And when we look at the second earthquake, it mainly caused higher spectral, the accelerations during at higher periods. And when we look at the directional effect, we can see that there are about 20% higher spectral accelerations when you consider directionality. So just to give you a complete picture, I will quickly show also the ground motion records measured at the greater Marash. So city center were somewhere there, and those are the stations around the larger, the wider the city. So on those stations, we observe higher PGAs, because some of those stations, this first earthquake, the rupture occurred on this fault line, and for the second one, the rupture occur somewhere here. So those stations are either the closer to the rupture fault during the first earthquake or the second earthquake. So overall, those stations recorded higher the PGA values. You see some of them here. Even in this station 4614, the PGA reached to 2.2 G. So extreme, the values for some cases, but again, those stations were not necessarily at the city center. But just for the complete list, I'm showing you those different, the ground motion intensity values for different stations measured around the Marash during this first earthquake. Again, as you can see, when we go to the northern part of the city, those stations really recorded very high spectral accelerations, and we see more stations where we have pulse-like ground motion records at those stations. And during the second event, this time, the second event, was occur on this Surgu Çardak fault, and this northern part of the station, the stations at the northern part of the city recorded higher PGA values compared to those stations in the south. And again, the spectral accelerations were really high for the northern part, but relatively lower for the south part of the region. And the directional effects were more pronounced, as you can see in this spectral acceleration plot for this region. So again, just to to give you the complete picture, the greater Marash experienced higher ground motion, or higher intensity of the shaking compared to the city center. And now, if we come back to the city center and try to understand what happened to those buildings that collapsed in the city center, so the first quickly, the Turkish building code, evolved during the years, and there were updates. The latest updates was in 2018. So some of those buildings designed based on the old codes, but some of them were relatively newer buildings. We need to consider that, and when we look at another important factor after 1999 earthquake in Turkey, this the building inspection law was introduced for 19 provinces as a pilot project, but only 3 of those provinces in the affected region were included on this pilot project. But in 2011, this building inspection law enforced for all the provinces, and in 2021 further improved by adding some more transparent regulations. So when we look at the 2007 code, the design spectrum, response reduction factor, and soil site classification defined in this code versus in 2018 code were different. So there were several changes here, but maybe one measure is the design spectrum. The ductile RC frames, the R was 8, and moment frame was 8, 6 for the shear wall buildings. They remain the same, but the definition of the R also changed. Definition of the site soil classes changed in this building codes. So there was also updates on the seismic hazard maps in 1994. Here you see the 4 different earthquake zones, and in 2018 there were more site-specific, the mapping of the hazard, and you were able to, to get your response spectrum values depending on your site. And other important thing to note is that the construction material quality also improved throughout the years. So some of the older buildings are using the less less, the quality material, just to keep this in mind. And when we look at the in the next slides, when we look at the effects of the earthquake in these different buildings, to help to assist the comparison, I calculated this design base shear, the ratio of the earth, the design base shear computed based on the spectrum, measured spectrum, divided by this design base shear computed following the building code, either 2007 or 2018 code. So here, if this ratio is less than 1, then the earthquake loads are smaller than the design loads. And if this ratio is greater than 1, earthquake loads are higher than design loads. So now, when we come back to the city center for the Marash, let's look at this image. So here you see a set of buildings. They were all, the collapse or demolished after the earthquake. Similarly, along the street, these buildings, they were totally, wiped out. And here in this region, only maybe a few buildings remain, but the rest were either collapsed or demolished. So let's again try to understand what happened, or what was the seismic demand during those earthquakes in the city center. So here are the stations. So those are the different, the buildings or the different streets that we have seen at the beginning in the city center. The closest, the station was this maybe 4620 station, but the other stations, I also included them for the analysis. And when we look at this design load comparison for kind of a typical RC moment frame building, we can see that for this if you compare based on the old code, 2007 code, you see this red lines, and when we look at the new code, we see higher ratios. The higher ratios means that the actually design loads were estimated to be lower, and I also show you both this ROT-D 100 and also the geometric mean comparisons for the calculation of the this ratio. So even you consider the ROT-D 100, we can see for this station at least this design loads were remain below the earthquake loads remain below the design shear loads. And when we look at this station 4621, now we see for a newer 2018 code, we see like a really sometimes high values, but for the old code, mostly below the design level. And similar things can be observed for these two soft soil stations, 4624 and 4625, where we had the higher ground motion records, but again they are located further south, closer to the rupture compared to this station and the city center. So when we look at this, the design or the earthquake load demands during the second earthquake, and now we see relatively higher the demands, but at larger period that is becoming the more prominent, and especially when you consider the directionality effects. And again, during the second earthquake, these two stations located in the south were away from the ruptured fault, and for them, this earthquake loads were even lower compared to the design load. But still, we had quite significant, significant effects during the second earthquake. And in this video, you see one building here on the background. This is during the second earthquake, and it will collapse at the city center of the Maras. You see this building is shaking, maybe with a kind of a short story here. But this building at the back has collapsed during this second earthquake. So although this, the design loads were lower during the second earthquake, first, the second earthquake had larger demands for higher periods, and considering that the second, during the second earthquake, the buildings had damage and their period has lengthened. That might have contributed to some of the damage observed. And another factor is actually the city of the Marash, originally, established at the outskirts of this, the mountainous area, but then with the time moved to the valley, and most of the buildings later then designed on the sulfur soil, on the alluvial deposition. So that's another factor contributing to failures. And when we look at the design of those some of those buildings in the city center, you see this the ground floors, which are set back from the upper floors, usually used for commercial purposes. That might have also contributed to some of the soft story failures observed during the events. And of course, look at these three buildings in this image. These three buildings designed and constructed at the same time, maybe by the same company. But when we look at these two more regular buildings, the irregularity in the plan might have contributed to the collapse of this building here. And when we look at some of the RC shear wall buildings, those are relatively newer buildings located again close to the city center. We see these 15-story buildings, and we also observe the damage collapse. Actually, two of the buildings collapsed during the earthquakes, and some of them just demolished after the earthquake. So there were a station just 3 kilometers away from this region, these buildings. And when we look at the demands, again, those are the buildings designed between 2015 to 2018. So probably they designed according to the 2007, the code, where we mostly estimate estimate a kind of a design level demand for those buildings. But notice that the higher demands for the 2018 code, that is because this 2018 the code, although the short period spectral accelerations increase in the long period region, mostly we see a decrease for the new the seismic map values for the design spectrum. So that might be the reason for that. And of course, for the damage for these buildings or the collapses, one reason was the poor construction practices. Here you see the damage on the shear wall, not enough concrete cover, not good detailing in this shear wall might have contributed to the collapse of this building. So some of the hospital buildings in the city center. So here we see Kahramanmaras City Hospital constructed in 2012, an RC shear wall building, and the hospital, the structural system remained intact, but there was significant non-structural damage, and you see the demands on this building, so they were even below the design level demands. And another hospital, this is also in the city center. This is an RC frame shear wall building, relatively older building, but this building performed quite well from the closest station. If we just look at the demands, they were considerably lower compared to the design based shear. And here is another hospital building, again in the city center. This building, there were not significant the damage, considerable damage on the structural system, but significant non-structural damage observed in this on this building. And actually, this building was demolished after the earthquake. But when we look at the demands on this earthquake, again, the demands were quite low for this building. So it's not expected to have such extensive damage in this building. So now I will quickly talk or go over some of the ground motion records recorded in Malatya, another district. Here are the available stations in Malatya. Again, from the first and second earthquake, we have the ground motions recorded at select stations, but the city center for this case corresponds to this location here, where we had actually a station, but neither during the first earthquake nor the second earthquake we were able to get any measurements at the city center. So the first, I want to show you all the ground motion records from all the stations. Only this 4406 during the second earthquake had ground PGA values higher than the design PGA level for this city. And when we look at the PGV values, they were the high for some of the stations. And mostly near to or closer to rupture the faults. And RES intensities were considerably lower for most of the stations compared to this 4406 station during the second event, where we have higher RES intensity, and the significant duration for those records, they were almost all all over. For different stations we have different durations, and the predominant periods similarly there were not as a kind of a trend for those the stations. And when we look at the spectral accelerations, now I show you the spectral accelerations for the first event and the second event, second earthquake. Again, the second earthquake caused the higher impact to this region. So you see the spectral acceleration during the first event. Here you see the spectral acceleration during the second event, and the highest spectral acceleration measured in this station 4406. And here are the vertical spectral accelerations. And the spectral velocities, again, they were relatively high, but not as high as the Marash during both during the second earthquake. I don't show you the first earthquake because during second earthquake it was like the intensity of the ground motion was higher. So now when we look at the city center, again, we will be focusing on the city center, and we will look at the performance of some of the buildings in the city center. This time we don't have that many stations nearby. The closest one was about like a 30-kilometer away from the city center. This 4406, 4412, and 4404. These three stations recorded ground motion records during both events, but this 4408 and 4413 just recorded during one of them. It will be great to get a record during at this station 4408 during this the second event. This second event, the rupture was along this fault, and this station 44.8 is up there, but we don't have any recording for this station during the second event. Again, looking at this rupture faults during the first event, here the rupture fault. So this station probably we will see higher the spectral values during the first event, and for this second event, these two stations are closer to the rupture fault, so we will see higher spectral accelerations in this slide. So the red is the first event, blue is the first earthquake, and the red is the second earthquake. The second earthquake again caused more, the impact in the city, in this particular city. And you see both the road D100, also the geometric mean of the two recorded horizontal ground motion records in this slide. So this 4406 is the highest, the station where we have the highest spectral acceleration. So again, we will look at the performance of some of the buildings at the city center. So here is the city center. The closest two stations are there, and we will look at the three buildings at this location and their performance. those are relatively newer reinforced concrete residential buildings. This is an 11-story building. After the earthquake, there were quite, the damage, both non-structural and structural damage in the building. Here you see the damage on this shear wall. And here is another building, a 12-story building, again in the city center. Here is an image during the construction of the building. After the event, here again, those photos were taken by a group of Turkish faculty who visited the region under the leadership of the Professor Erkut Sayın. And you see again those shear wall damages in this building after the earthquake. There was another building where actually collapse occurred. Again, the same site, the same location, a 12-story building, which they also got some attention in the media. So in that case, this building had actually a kind of a soft story collapse during the earthquake. Look at this second pair of this building. It just survived, but the second earthquake had the soft story failure during the earthquake. And when we look at the demands from these two events in the city center, the demands are during when we compare 2007 and 2018 codes, again this 2018 code is providing maybe smaller shear designs, therefore larger seismic demands. Here we see, but for the older code they are lower. However, here notice that most of those events are those buildings were relatively new. So I am here comparing the seismic demands during the first earthquake and second earthquake, considering only just this newer seismic maps, newer building code. And here you see the demands on this RC frame shear wall buildings for this period range of 0.8 to 1.6. Remember, all the buildings were mostly 12-story buildings. So what we can see, the demands were either around the design level or lower. But the second, we have the second event higher demands. This first earthquake, they had smaller demands on the building. So if we look at this same region, that I showed you some of the examples after the earthquake, many of these buildings, that were tagged, the heavily damaged. They were actually destroyed or demolished. So here you see just a video of from this demolition. And very quickly, I will also show you an example of the shear wall buildings that were further north of the city. Those are like a 15-story buildings mostly. I don't have many, the information about the damage observed in this building, but that's one of the photo that I have seen. And maybe from this photo, we may infer some settlement issues in this particular building. But those are the shear wall buildings. When we look at the demands, they were lower than the design level demands, but those buildings, those 11, 15-story buildings, all of them were also demolished after the earthquake. So that is a video showing this, the demolition of these buildings after the earthquake. So those buildings were relatively older, so they were designed or constructed starting from 1994 up to the 2000s. So they were relatively older, but all shear wall buildings, they were demolished. Here is a 10-story building that remained, but 11, 15-story buildings were demolished. And very quickly, I will also show you the performance of 3 base isolated buildings in the city center. Those 3 buildings were in the city center, isolated with the friction pendulum bearings, different capacities. They are mostly relevant, relatively new buildings, and those buildings perform quite well. There were some issues in two of the base isolated buildings, but those issues were mostly due to the issues like this closing the seismic gap, the moat covering them, preventing the movement of the building. Otherwise, as far as reported by the producer of the isolators, the isolation systems perform well, except in some of those buildings where the movement of the isolators were prevented. And when we look at the demands on these buildings, they were, the isolation system is affecting, reducing the demands about 10% of the earthquake demand. So if we conclude, so we can see that the buildings that are 10 to 11, 15-story height, located on soft soils were vulnerable. The buildings where we have soft stories at the ground floors were among another group of the vulnerable buildings. The poor construction practices, low quality construction materials contributed to the failures, especially in older buildings. Also, we need to note consider the compounding impacts of the earthquakes. And the hospitals, the either fixed or the isolated buildings structurally perform well, but the non-structural damage observed, especially in the fixed-base buildings. It's also important to account for the directionality. Like there were about 20 or 30% increase when we considered directionality in the seismic demands. And this latest code, the 2018 code, and the seismic maps are usually estimating the high period demands lower compared to the previous seismic maps. So that is something that deserve more attention. And finally, I want to highlight that this, the concept of the functional recovery is really not a luxury. The many of these hospitals, they had to to perform after the earthquake, and the isolation system. We have seen that one effective way of achieving this immediate the occupancy functionality in those hospitals if the isolation system is being applied correctly. And also this concept of the functional recovery is important, not only just these important buildings, but we see that in these urban areas we have a high population, and this demolition or the heavy damage in many buildings are causing really high social consequences. So achieving a high performance levels will be important for the future. So with that, I want to thanks again for the Lehigh team for the invitation, and if you have any question, we can maybe go over some of the questions.
So are there any questions from the audience? Sorry, go ahead, Tommy.
Yeah, I was gonna say at this time, if anybody has any questions, you can either put them in the chat in the Q&A or raise your hand and we'll allow you to talk.
Osman, I had a question, but I can wait for the audience to ask theirs.
Sure.
Well, maybe what I'd like to ask is, I noticed, as you mentioned towards the end of your presentation, the base isolated structures, they tended to perform reasonably well, but the non-structural, so basically the structure is dysfunctional. Do you have any sense what you could attribute that to? Are there still acceleration, say, in the higher modes that cause that? The interior contours as well as the cladding seem to both be damaged in some of those hospitals. Or was it primarily interior contents?
Yeah, for one of the base isolated building in the city center of the Malatya, actually there were not even considerable non-structural damage, so that performed well. But that the isolation system Also, like the application of the isotope was more proper. There were no blockage of the mode, so it performed quite well, and it was able to reduce the non-structural damage as well. Two of the hospital-based isolated hospitals were where we have seen some non-structural damage were mostly, there were some issues in implementing or like the seismic gap either filled with the gravel or with a kind of a pavement, so the movement of the building was prevented. I think that was one of the reason for one of the hospital that they observed quite the considerable non-structural damage, but all those isolated buildings remain functional and operational after the earthquake. The fixed buildings, hospital buildings, some of them had really significant non-structural damage and had to be closed after the earthquake.
So the non-structural, I mean, evidently must have had higher accelerations inside the structure, even though it was basically isolated. I guess the first mode is isolated. There's still some higher accelerations that developed.
So yeah, unfortunately, in none of those, the three buildings, we had any instrumentation, so we don't have the acceleration.
I understand.
Yeah.
So you mentioned friction pendulum systems, but what were the vertical accelerations in those areas that those systems still performed well?
So in the overall region, at certain locations, there were really very high vertical accelerations. But for this particular city center, vertical accelerations were not necessarily that high. Actually, the ground motion records, the PGA levels were also not necessarily too high for this particular city. But there were some other cities where we had isolated buildings, also the high vertical accelerations, but I didn't, to go over those examples in this presentation.
Okay, sorry, one last question, because there's some others I don't need to ask. So in some of those isolated structures, were there any velocity pulses observed in records, say, that were recorded nearby to any of those base isolated structures? And if so, how did those particular isolated structures perform compared to others that were further from faults?
Yeah, I think there were several such hospitals where they were relatively closer to the fault, but those were under construction, so they were not completed. So we don't have a full understanding of their the response during the earthquake. But for these two cities, in particular, we didn't have a base isolated building very close to the ruptured fault.
Oh, okay. Let me go ahead and read some of the questions in the chat box there, Osman.
So if you could take care of the Q&A and questions, that would be great. I do have to run to another meeting, so
okay,
it's open, but if you could handle that, I appreciate it.
Okay, so the first one is by Amin, and he asked, did you apply any modifications to the AFAD's ground motions, or you directly use the processed motions?
Yeah, AFAD or the AFAD is the Turkish equivalent of the FEMA, and they provided the ground motion sets actually used also in the data base of the design safe. But so the ones that I use for the AFADs, the ground motions, I use their process acceleration record. So yeah, it was process acceleration record or the corrected acceleration record, where I further process and obtain the different intensity measures.
Okay, and then the next one is anonymous, so we'll give credit to whoever that may be. It's related to the fact that they appreciate your presentation, very nice, and then asked something related to the fact that you mentioned directionality effects and the importance, for each station.
Yeah.
Where the records basically measure the different orientations and compute the ROT-based demands.
Okay, so yeah, that's a good question. So so the reason that I include this ROT DE100, the measurements, is that I just want all of us to understand how intense was the shaking in those cities. and the recorded ground motions are not necessarily, they are only in two directions, and the buildings may be subjected to those ground motions at any direction. By computing the rod D100, which is the maximum direction, like for the record, we can get an understanding what could be the highest intensity of those ground motion record. And once you have this two orthogonal component of the records measured from one station, you can easily calculate the ground motion record at any other directions. So, but the main motivation for including the rod D100 was just to illustrate what will be the highest possible effect from those records.
Okay. Now, the next one is Samorali, 2009. That's his email, person's email address. I'd like to know what can you say about the subsoil? You know, I quite understand the question, but can we say that the subsoil had the most effect for damage? I guess the effects of soil structure interaction.
Yeah. So definitely the soft soil amplified the ground motion records. For these two cities, maybe for they were not that apparent, but for some other regions in the affected larger region, we see this more clearly. For the Marash, again, this like the two of the stations where we have the soft soil, we have seen larger or amplify the effects. And for the other question, I think the other part of the question is about this comparison of the two seismic, or the design codes, the NHERI, the code. My observations is that at higher periods, it just provides lower spectral accelerations. If you have a design spectrum constructed by the NHERI code, it tends to to provide lower level at higher periods.
Mm-hmm. And then so as a follow-up to that, do you think the codes should be modified?
To be honest,
Density level.
yeah, like my study was not that extensive to make this, the suggestion necessarily, but I have seen in the literature as well, some of the previous work indicated that this longer periods in the NHERI code has lower spectral acceleration. So definitely it requires closer attention, but it's not necessarily an area of my expertise. So I'm sure that the Turkish colleagues will look at this more carefully.
And then two other questions there, Osman. So there's a question from ESCM. And basically this person asked, was the predominant direction of the first and second earthquake significantly different orthogonally? Not worded right, but
yeah. So like it kind of varies to the predominant direction. I didn't pay attention because I also calculated the rod D100 because the buildings that we have, we cannot necessarily say that they will be subjected to one of these two directions. The buildings can be subjected to any of those directions. So that's why I calculated this rod D100, the maximum direction, so that can provide us a better idea like what will be the maximum effect on the buildings.
Because I guess it's going to depend on the principal axes and minor axes of the building and orientation relative to how the P and the shear waves are traveling, right? So the orthogonality is just basically an envelope of what could possibly happen depending on the orientation of the various buildings. Anyway, so the last question here, Osman, is in the local design codes, are the pulse effects considered to estimate for a design gap of isolation systems?
That's a good question. I'm not sure how that is being addressed, but I am assuming that there might be some, the additional considerations for the buildings located near fault regions, especially the isolated buildings. But I'm not sure about the details of this provision.
Okay. Well, I think with that, probably we should close. I just want to say a few other things. And first, thank you, Osman. I think all the audience thanks you as well. You're getting a lot of thumbs up there. I thought it was just very interesting. Seems like there's still a lot more work to be done there, particularly with the concerns that people have for earthquakes. And so Osman, I just tell the audience, I know you from the fact that you've attended our researcher workshop. So I want to encourage the audience to Google NHERI Lehigh and come visit us if you can. We have researcher workshops. Osman did that and has several projects in her laboratory committed towards making a community more resilient to earthquake effects. So if you visit our website, you can get more information about our site. We have an upcoming researchers workshop in November 16th and 17th that I again encourage you to attend. There is some travel support for those that are interested in submitting proposals. And I think with that, we should go ahead and close there, Osman. And again, I wanted to thank you for doing this. And I know it's a little bit later there where you are, but it seemed like it worked out okay there.
Thank you so much. And sorry for going a little bit over in the time, but I appreciate the opportunity. Thank you.
A lot of information, I think, to provide it. And I think if the audience has any other questions, they can probably follow up with, basically connecting with you by email. Our particular, the seminar is recorded, and we have it archived on our webpage, or it will be. So those that want to go back and look at it later can do so, as well as prior seminars. And our next seminar here will be, I think, next month in a few weeks here. I don't quite have all the topics, but one of them will be a machine learning committed towards structural health monitoring. And another one is supposed to be related towards coastal community resiliency and looking at fluid structure interaction type effects. Okay, well, thank you again, Osman. So we'll keep in touch and talk to you soon then.
Thank you, Jim. Bye-bye.
Yeah, thank you. Bye. Joe, I assume I can just go ahead and log out here if you're still there.
Yeah, I'll close it off. Thanks.
You're gonna close it up, okay.
Yep.
Okay, so I didn't want to cut it off if it's supposed to be recorded there. And I think we're gonna meet with Mohammed there, I think, soon here. I have it on my calendar here.
Yeah,
Okay.
yeah, it should be pretty quick.
Okay, I'll let you all go then. Okay, talk to you. See you
All right.
later there, Ollie.